Have you ever stopped to wonder what's holding the atoms in your body together? Or what exactly unleashes the incredible power of a lightning strike? Well, the answer is this invisible force, a sort of unseen architecture that governs our entire universe at the most basic level. And today, we're going to dive deep into this hidden world. The area of physics we're exploring is called electrostatics, and really the name gives it all away. Electro for electric charge, and statics meaning at rest. So we're basically looking at the rulebook for electric charges that are just sitting still. But you're about to see that their influence is anything but static. So this is the big question we're going to tackle together. We're going to build our understanding right from the ground up, starting with the very source of this power, and we'll end up with the incredibly elegant laws that describe how it all behaves across the entire cosmos. Okay, so to understand the architecture, first you have to understand the bricks. And in the world of electricity, that fundamental building block, that single brick, is something we call electric charge. You know, what's so fascinating is that charge isn't something you add to an object, like painting a wall. It's an intrinsic part of matter itself, just like mass is. It's built in, and its whole origin story really boils down to one tiny particle, the electron. And it's such a beautifully simple system when you think about it. If an object is neutral, it just means it has a perfect balance of protons and electrons. But if it loses some of those electrons, it suddenly has a positive charge. And if it grabs a few extra electrons, boom, it's got a negative charge. That's really it. Every bit of electric charge comes from this simple imbalance. All right, so we've got these two types of charges, but how do they, talk to each other? Let's get into the fundamental rules of how they interact. This is the one we all learn pretty early on, right? It is the bedrock of electrostatics, like repels like and opposites attract. A positive charge will literally push another positive charge away, but it will pull a negative charge in closer. And this one simple rule is responsible for so much. Everything from the static cling on your clothes to the chemical bonds that make life itself possible. But there's a little more to it than just a simple push and pull. Charge has these three completely unshakable properties. First, it's additive. You just add up the positives and negatives to get the total. Super easy. Second, it's conserved. You can't just create or destroy charge out of thin air. You can only move it around. And finally, it's quantized. And this is where things get really interesting. So what does quantized actually mean? It means charge isn't some continuous fluid you can just pour. No, it comes in tiny, indivisible packets. You can have one of these packets, or two, or a billion, but you can never ever have half a packet. The number right here, that's the value of that one fundamental packet. It's the charge of a single electron. Every single charge in the universe is a whole number multiple of this tiny amount. It's kind of like a digital currency for the entire cosmos. Now, knowing that charges push and pull is one thing, but physics demands precision. We need to know exactly how much they push and pull. And that brings us to one of the absolute cornerstones of physics. Before we even look at the math, let's just appreciate the logic here. This is Coulomb's law, and it tells us two really simple things. One, make the charges stronger, and the force between them gets stronger. Makes sense. Two, move them farther apart, and the force gets weaker. And not just a little weaker, but weaker with the square of the distance. So if you double the distance, the force drops all the way down to 1/4 of what it was. And here it is. That whole relationship captured in a single, elegant equation. With this one formula, we can calculate the exact force between any two charges anywhere in the universe. It is the mathematical key that unlocks the entire field of electrostatics. So Coulomb's law is incredibly powerful, but it also brings up a really deep question. It describes a force that acts across a distance, but it doesn't really explain how. I mean, really think about it. How does a charge way over here know that another charge is way over there? They aren't connected by a string or anything. This question pushed physicists toward one of the most profound ideas in all of science. The answer? The electric field. See, a charge doesn't directly pull on some distant charge. Instead, it actually alters the very fabric of the space all around it. It creates this invisible field of influence. And that field is what exerts a force on any other charge that happens to wander into it. The field is the messenger. And we can actually visualize this invisible field by using a tool called electric field lines. You can think of these lines as a weather map for electric forces. They show us which way the force would point, and the closer they are together, the stronger the field is. They literally show us how charges communicate their presence across empty space. The electric field is a totally revolutionary idea, but it turns out there's an even more fundamental law lurking just beneath the surface, one that reveals a really stunning symmetry in how our universe is put together. Now, to get this deeper law, we need one more concept: electric flux. Okay, imagine you're holding a big net out in a windy field. The flux is just a way to measure how much wind is passing through your net. Electric flux is the exact same idea. It's just a measure of how much of the electric field flows through any given surface. And that brings us to the big one, Gauss's law. This is honestly one of the most powerful and beautiful statements in all of physics. It says that if you draw any kind of imaginary bubble anywhere in space, the total electric flux flowing out of that bubble depends only on the total amount of charge that you've trapped inside it. And there it is in mathematical form. Look how clean that is. It's so simple, but it's incredibly deep. That symbol on the left, that's the net flux, the total field flowing out. And on the right, that's the total charge inside the bubble. It connects the cause, the charge, directly to its effect, the field. And here is the key insight, the part that's so profound. It does not matter if your imaginary bubble is a tiny perfect sphere or a giant lumpy potato shape. It doesn't matter where the charges are scattered around inside the bubble. The total outflow of the electric field is always the same, as long as the total charge inside is the same. It's a fundamental truth about the relationship between charge and space itself. So we've gone from a simple push and pull all the way to the deep geometric symmetry of Gauss's law. It proves that the universe is governed by these rules of incredible elegance. And it leaves us with this final, really tantalizing question. If a law this beautiful governs the invisible force of electrostatics, what other elegant rules are hiding just beneath the surface of our reality, just waiting for us to discover them?